Hey everyone, in this video we're going to be talking about journal bearings and specifically looking at Trumpler's design criteria and an example design problem. And this video is part of a lecture series on mechanical design too. So we're going to start by talking about Trumpler's design criteria. And what Trumpler did is he basically created some design criteria where you can design some bearings from scratch based on rules on temperature as well as minimum distances that needed to be checked and um, some pressure rules as well when the bearing starts to rotate. So we're going to get started with just describing some of the different things that he thought of when he was working on this type of problem and coming up with design criteria for bearings and for journal bearings specifically. And one of the first things is that bearings can rotate off center. So bearings do not, especially the type of bearing that we have, does not always rotate perfectly in the middle. So we have a journal and a bushing, and there's a very, very small gap between them. And sometimes the journal starts moving closer to the wall and rotates off center. And this creates a very small H0, which is our minimum film thickness. Okay. And our question that we can pose ourselves is, what is the minimum HO we need to be able to have rotation and not have any problems with friction? So our question that we can pose ourselves and that Trumpler posed himself is, what is the limit of HO? Okay. And the limit of HO is essentially that HO has to be big enough so debris, or the smallest debris of metal debris, for example, can pass and not block lubricant flow. So the next question you would ask me is, well, why would there be any debris? Okay, why would there be any metal shavings or anything that is a problem within the journal and bushing combination? And the reason why there's debris is because when you start the rotation, let's say we start the system from scratch, initially, what happens is when you start the rotation, because of gravity, your journal is usually, and I'm over exaggerating the size of the journal and the bushing just to show, but the journal would sit on the bushing surface. So as soon as you start the rotation, what happens is you can have some very, very small debris being created by this start of movement. So every time you start a rotation, we can say that some debris will be generated. And this is very, very small debris. We wouldn't be able to see it with the naked eye usually, okay? So it's very, very small. And what Trumpler did is he did some experiments and he started looking at, okay, well, if we have a journal and bushing combination, and we know that our value should be HO there should be a minimum value of HO. This minimum value should be the size, if we have a lot of debris rotating around, the minimum HO should be the size of the biggest debris essentially. Okay, so that it should basically allow all the debris to pass through. And what he came up with as a rule was that HO should be greater than or equal to 0.0002 plus 0.00004 times diameter, and this is in inches. Okay, so we can see that it's a very, very small value. Okay, so our HO should be a very, very, very small value. And now what we can do is we can use that as a design criteria to go into our tables and to go into our charts to find what our HO would be based on the diameter of our journal. Okay, now the next thing he looked at was the lubricant and what happens when you have your lubricant, and we can study a lubricant is usually a mixture of hydrocarbons. And what we mean by hydrocarbons is just hydrogen and carbon. So a very famous, any type of oil is usually a hydrocarbon, okay? And when you heat up a hydrocarbon, what you usually get is you get a loss in viscosity, okay? So what can happen is you could have a loss in viscosity. So as temperature goes up, viscosity goes down, okay? Our output, a viscosity goes down. Now, if you heat it up too much, what happens is it could self-ignite. So if you heat up oil too much, it could self-ignite, and it's a big problem. And another problem that can happen, and that is very unpredictable, is that if you take a lubricant and you heat up too much to the point where it starts vaporizing, what happens is our hydrocarbon is usually a mixture of hydrocarbon, or our oil is or our lubricant is usually a mixture of hydrocarbons, and some of them are called long chain hydrocarbons, and some of them are called short chain. And what happens is when you have a long chain hydrocarbon, you have, so let's say for example we had a 50% C8H18 hydrocarbon and 50% CH4 hydrocarbon. So if we were to draw these in terms of molecular structure, we would have carbon, carbon, carbon. We would have 8 carbons. And then all around those carbon, we would have H's. So I'm not going to draw all the H's, but we would have H's all around. So we can see that that's an example of a long chain, whereas a CH4 is just C with 4 H's around it. So I'll just draw the H's for this short one, but you get the idea for the long one. And a particularity of this is that when you have a long chain and a short chain, what happens is when you heat up the mixture, what happens is our short chain, so these ones, start to vaporize first. And this has an effect of increasing viscosity. So whenever we heat up an oil, typically we always see a decrease in viscosity. Our oil becomes more smooth and less viscous, okay? And that can be good or bad, but it's something that's predictable. But if you heat it up too much, what can happen is you can have a very drastic increase in viscosity, which would create an increase in heat generation, which would then result in failure. And so what Trumpler said is that for light oils, which is mostly oils that we would use in this type of application, our Tmax would be less than or equal to 250 degrees Fahrenheit. So what we try and do is we try to have our operation temperature to always be under 250 degrees Fahrenheit. Now, as of late, we've had some advances in light oils, and some oils can withstand a higher temperature, some oils can withstand a lower temperature. So it's important to check with manufacturer. Okay, so you want to definitely check with the manufacturer. But if not, a good rule of thumb is to try and keep your system under 250 degrees Fahrenheit. If it's above 250 degrees, you're going to have to look into specialty oils, or you're going to have to change your system to cool it down a little bit more. Okay. Now, the third thing that Trumpler looked at was when you have a start of rotation, which we talked about earlier. So when the system is off and you're turning it on, you want to limit the pressure in your system. So we know that pressure is equal to W over LD, or W over 2RL, okay? So what you want to do is you want to try and limit that pressure at the start, because you don't want the start force to be too high and the force to be too high all at once. So you're going to have to limit yourself in the force. So what we can change is here we can add a sub ST for start. Okay, let me just redraw it really quickly. Okay, so WST over LD should be a certain value, and this certain value is going to be less than 300 psi. So this is another rule, that your LD should be less than 300 psi. And then one last rule that he has is ND should be greater than 2 while running. And what the ND is essentially a safety factor of 2, which we're not really going to go too much into, but it is a design factor, or a number of design which should be greater than 2 in this case. The last thing that he also said is he also uses temperature average for calculation. So you have, for example, if you have a bearing like this horizontal bearing with a journal and a bushing around it. So we have the journal in here, and we have a bushing here. Okay, and all this is our liquid film. Okay, if you have an entrance, you're going to have an outlet like this. You're going to have outlets like this, and what you can do is you can measure the temperature at the, so we'll write this as outlet, and this here is inlet. And what you can do is you can measure the pressure and say that the temperature, and you can say that T average is equal to T1 plus T2 over 2. Okay, so we find the average temperature in our system. We can also write that delta T, sometimes you'll be given a change in temperature, is going to be equal to T2 minus T1, or temperature raise or temperature increase. So we can also write that Tav is equal to T1 plus delta T over 2. It just means exactly the same thing. It's just sometimes in problems you'll be given this temperature increase. You'll be told, for example, the temperature of the fluid going in is 300 degrees Fahrenheit, and the temperature increase is 50 degrees Fahrenheit. So then you know that you're dealing with a temperature increase, so you can use that equation to find the T average. Okay, and that T average should be under 250 degrees. Okay, so what we're going to do now is we're going to apply this Trumpler's rule to an example problem. And we're going to do this now, and we're also going to do this in the next video as well, another example, just so that we can practice and we can really understand how to use his conditions. Essentially, what we're trying to do is we're trying to use Trumpler's design criterion as well as stable lubrication to solve our problems, because that's what we know we need to kind of define when we're looking at designs. So I'm going to copy over the problem, and we're going to get started on that problem. So this is a problem that was designed for an exam in mechanical design 2 as well. So it could be useful for exam preparation as well if you're taking an exam on that as well. So you are designing a bushing with a diameter of 1.002 inches and a length of 1 inch. Okay. That interfaces with a shaft that has a diameter of 1 inch. So we understand that we have a 1 inch diameter journal, we have a 1.002 inch bushing, which rotates at 1200 RPM. Estimate the maximum operating temperature if you're using SAE40 lubricant if the system is required to maintain stable lubrication under the conditions prescribed by Trumpler's criterion. So I'm just going to underline here, if it lets me. Let me just underline stable lubrication, and I'm going to underline Trumpler's design criterion. So those two things are things that we have to satisfy. What is the value of friction coefficient of your lubricant at this temperature if the maximum allowable load is applied to the shaft? And what is the loss in power due to the lubricant under these conditions? And would you recommend using this setup outdoors in Miami throughout the year? So let's try and think of this, and let's go ahead and answer the first question. So what we're told, let's write some information down first. But essentially what we're told is we have to estimate the maximum operating temperature if you're using SAE40 lubricant. So that's our first thing that we have to figure out. And we're going to do this in two different ways because we don't really have any design criteria yet. We just have the geometry, but we don't really know what to do next. Okay, so first things first is we're going to write all our information down. So we have that diameter is equal to 1, L is equal to 1, B is equal to 1.002, and N is equal to 1200 over 60, and that's going to be in RPS. Okay, we know that we have SAE40 oil, and we can calculate our clearance is B minus D over 2, which is going to be 0.001 inches. Okay, and we're told that our system has to follow the following criteria. So it has to follow stable lubrication and Trumpler. So I'm going to call criteria 1 stable lubrication, and criteria 2 I'm going to call Trumpler's criteria. Okay, and these are also available in your formula sheet, so you can have access to them in your formula sheet as well. But stable lubrication is the first one. So we know that stable lubrication, we need to satisfy that UN over P should be greater than or equal to 1.7 times 10 to the minus 6. Okay, we have that information, and the good thing with that is that we can design based on this information as well. Trumpler's criteria, on the other hand, has a Tmax of less than 250 degrees Fahrenheit. It has a W ST over LD less than or equal to 300 psi, and we have an H0 is greater than or equal to 0.0002 plus 0.00004 D in inches. Okay, so those are our two criteria. And what we can do is we can say, well, there's two different ways we can go about this problem. We can start by verifying what criteria 1 is and then solve some things for criteria 1, or we can start verifying what criteria 2 is and how we can maintain criteria 2 and then try and solve our problem using that one or the other as our starting point. And once we satisfy one criteria, we need to check for the other one. Okay, so I'm going to do this problem both ways. I'm going to start with criteria 2 first, and I'm going to try and solve it with criteria 2 first and then check if it satisfies stable lubrication. And then vice versa, I'm going to do criteria 1 first and then check criteria 2 second. Okay, so we're going to start with first solving it with criteria 2. So here we basically need to pick a criteria that we're going to use to design our system. Okay, so we're told that we are designing a bushing with this diameter. So we're told that we have to estimate the maximum operating temperature under the conditions prescribed by Trumpler's criterion. And we're also told that the maximum allowable load is applied to the shaft. Okay, so we're told that we are going to have the maximum allowable load applied to the shaft, which is probably going to have something to do with this. Okay, but we'll come back to it in a second. So first things first, since we're using Trumpler's criteria to design the system, what H0 should we use? Well, we know that the minimum H0 should be equal to or greater than the value up here, okay? And since we know that that's the minimum value or greater, what we're going to do is we're going to use the minimum value, okay? We're going to use the minimum value as our design criteria to start with. We can change it later if needed, but we're going to start with this minimum value of HO is equal to 0.0002 plus 0.000004 times D, and D is 1. So we're going to get that HO is equal to 3 zeros, 24 inches. So we have a starting point for our design. The other thing we're told is that our load in the question, we're told that we're going to use the maximum allowable load applied to the shaft. So the maximum allowable load applied to the shaft is when pressure is equal to 300 psi. That's the maximum load that we can apply to the shaft based on Trumpler's criteria. So that means that 300 psi is equal to WST over LD, and that means that I can convert this to WST is equal to 300 times L and D, and L and D are 1, so we get that WST is equal to 300 pound force. Okay, so that helps us a little bit. Now, what we can do from this is we can actually work in reverse on our chart, and we can find S. So instead of finding S from, let's say, R over C squared times mu N over P, okay, we know that S is equal to that. We can find S from H0 instead. So because we have a value of H0 already, we can actually find S from the chart working backwards with H0 that we already have. So we can say that H0 over C on our chart is going to be equal to 0.00024 divided by 0.0001, which is going to give us a value of 0.24. Okay, and I can go to my chart and find S that way. So we're going to go look and try and find S that way. So we know that our L over D is equal to 1, so that should help us in our chart as well. And we can go find S. So let's go find S in our chart. So if we go to Module 4 formula sheet, we're going to go to the H0 over C term. And what we're going to do is we're going to work backwards to find S. So we know that we have L over D is equal to 1. And we have that H0 over C is 0.24. So that means that it's right here. So if we go over, if we move over, we get that our value is somewhere around here, which brings us to a value of down here for S. And we can say that S is equal to 0.055, okay, or close to that value. So I'm going to write my S value in my notes, saying from the chart, we found that S is equal to 0.055. And for now, what we're doing is we're designing a system that satisfies Trumpler's criteria and Trumpler's criteria only. Okay, we haven't found if it satisfies stable lubrication. We'll have to check that later on. Okay, so we have that S is equal to 0.055. So the next thing we can do is we can find mu, so that we can find mu from our S equation. So we know that S is equal to R over C squared. We have R, we have C, and then multiplied by mu times N over P. And we already have pressure and we already have N. So the only thing that's left is we have mu that's left to find. We also have S, so I'll just check S. And so if we rearrange, we can find our mu from there. So we can say that based on Trumpler's criteria, mu would be equal to 0.055, not 0.55. Let me correct that. Multiplied by 0.001 over 0.5 squared. Okay, and then 300 over 20, which is our RPS. Okay, and we get that mu is equal to 3.3 times 10 to the minus 6 reign, which we can convert to micro reign if we want. So we can write that mu prime is equal to 3.3 micro reign. And based on that, so we can say that according to Trumpler, solely based on Trumpler's criteria, we can say that Tmax can be found from our mu. So we can go to the charts once again. So we're working backwards in our problem because now we're designing. We're not given a design and trying to find values. We're actually designing and working backwards to find what our Tmax is. So if we go back to our formula sheet and we go to the first page of our formula sheet, on the left-hand side, we have the different oils. So we know that we have SAE40 oil, and we know its absolute viscosity as dictated by Trumpler's criteria. So we have 1, 2, 3.3 is going to be between these two lines here. I'm going to zoom in a little bit. So it's going to be anywhere between these two lines, and we're going to have a value that's going to be around this value right here, which if we go down and look down, we have, it's going to be a little bit to the right there. So it's going to be around somewhere around here. Okay. So we have 165 Fahrenheit or 163, 62. It's up to you how you want to do it. It's pretty close anyways, but we're going to have a Tmax as our value that is equal to 165 degrees Fahrenheit. Okay. Now, before we move on to finding all the other stuff, we need to first, so before finding all the other stuff, we need to say, okay, Tmax is equal to 165 according to Trumpler. Okay, we're still just according to Trumpler. The next thing we need to do is figure out, does it satisfy criteria 1? Does it satisfy stable lubrication? Because if it doesn't satisfy stable lubrication, we need to use stable lubrication as our guiding principle, basically. Okay, so if we look at criteria 1, we have that mu n over p should be greater than or equal to 1.7 times 10 to the minus 6. So let's actually figure out what our values of mu should be. So based on this, we're told that mu should be greater than or equal to 1.7 times 10 to the minus 6, okay, which is the right side. And then we're going to move the n and p to the right side and see what mu value would satisfy. Another way to do it is to say, well, let's just plug in the mu that we have, which is 3.3, and plug in and see if we have greater than 1.7. But you'll see that that's not the case. So if we multiply by 300 divided by 20, we get that mu should be greater than or equal to 25.5 times 10 to the minus 6 rane. So now we know that we can write it in a different way too. So this is a requirement that we have. Okay, so this is requirement. And we can say that Trumpler did not satisfy this requirement. Okay, another way we could have done this is we could have said, let's just plug in our values for Trumpler into mu n over p. So we would have 3.3 times 10 to the minus 6 times 20 divided by 300, and we would have gotten an answer of 0.22 times 10 to the minus 6, which would have been less than 1.7 times 10 to the minus 6. So we could have said not stable. So that means that we need to figure out, based on our information, we need to figure out from the chart how to satisfy Trumpler, but also satisfy a Tmax that is appropriate for stable lubrication. So we're going to go back to our chart and find a Tmax that is appropriate for our lubrication. And that Tmax would be 25.5 times 10 to the minus 6. So we're going to go back to our chart, and we're going to go see at a value of 25.5. So a value that is up here Okay, and I'm just going to use a line because it's so close to 25.5 anyways. And we're going to find where it intersects with SAE 40. So we have somewhere around here. And if we go down, we'll see that that's around here, which is 95 degrees Fahrenheit. So I'm going to write that Tmax should be 95 degrees Fahrenheit. Okay, and this is really our satisfaction. So that means that our Tmax is 95 degrees Fahrenheit to satisfy stable lubrication as well as Trumpler's criteria, and therefore we need to use SAE 40 oil at 95 degrees Fahrenheit, not hotter than that. If we use hotter than that, we have a problem. Okay, now there's a second method in which we could have solved this problem. Okay, and so the first method we used criteria 2, then criteria 1. The other way we can do this is we can say, well, let's solve for criteria 2 first and then criteria 1 after. Okay, so doing the opposite essentially. And then we can answer all of our questions subsequent. Okay, now obviously, if you're given this problem in an exam, you don't need to show me both ways. Once you're done with this first way of doing it, then you could have gone to answer part A, part B, and part C, or the 3 other questions in the question. But I just want to show you the second method. That would be inverted to start with stable lubrication and then go and check for criteria. Okay, so let's say we were going to check stable lubrication first. So I'll put method 2 here of solving. Okay, we're going to start with criteria 1. Okay, so method 2 of solving, we start with criteria 1, stable lubrication, and we say that mu n over p should satisfy greater than 1.7 times 10 to the minus 6. And because of that, we have that mu would be equal to 25.5 times 10 to the minus 6 based on the information that we have of n and p, and we can make it equal to the minimum value for stable lubrication. And that would yield us a Tmax of 95 degrees Fahrenheit, something that we've already done, but we're doing it now in reverse, so we're redoing it just to show you. So now what we can do is we can say, well, if this is the case, if the case is that we have a stable lubrication at 95 degrees Fahrenheit, then let's check for Trumpler's criteria and make sure that Trumpler's criteria is satisfied by checking that Trumpler's criteria is actually satisfied within the bounds of what we have. So we can say that the next thing we can do is we can calculate S based on this viscosity. So we can say that S is equal to 0.5 over 0.001 all squared. And then we're going to multiply by 25.5 times 10 to the minus 6 times 20 divided by 300 based on the information that we're given. Okay, so far we've only checked for stable lubrication. Stable lubrication works. So now we're going to check that it matches with Trumpler. Okay, so we're checking that it matches with Trumpler, and essentially what we're checking is that Tmax is less than 250, less than or equal to 250 F. Okay, which is already satisfied. Okay, we're at 95 degrees Fahrenheit, so that should be good. Then we are going to check that WST over LD is, or the pressure is less than 300 psi. Okay, that's a given, and we're given that in the problem, so that's also a check. Okay, we're given that we can use that as a power, so we already chose as a load, so we're going to use 300 pound force as a load, so we know that that's satisfied. And the last one we need to satisfy is HO is greater than or equal to 0.00024. Okay, and that's really the last one that we have to check. And we can check that based on our stable criteria. So we have, for our stable criteria, we have that S is equal to 0.425. And based on that, we can go to our chart and solve for H0 over C. And our H0 over C, if we go to our chart based on this, at 0.425, which is somewhere around here, a little bit lower than that, but pretty close. is going to be equal to, 0.425 being the S value is going to be 0.4244, no, so 45.5. So it's going to be somewhere around here. We're going to go up to 1, and we're going to be up here. So we're going to have a value that's going to be somewhere close to up here, which is going to be a value of around 0.72. Okay, so our value is going to be up here somewhere. So just let me show you again. So we're going to have a value of here of 0.425. Then we're going to be close to here, which is going to yield a value of 0.71 or 0.72. Okay, so we're going to write 0.72 here as our value. And since H0 is equal to 0.72, we can then find HO is equal to 0.000 times C is going to be 7.2 inches, which is going to satisfy our Trumpler's criteria. So that means that with a Tmax of equal to 95 degrees Fahrenheit, we satisfy 1 and 2. So we satisfy Trumpler's criteria as well as stable lubrication. So now what we can do is we can solve the rest. Okay, so we can solve the rest of the problem. Now, the method that I showed you second is the preferred method. So you always want to try and start with your stable lubrication. Okay, because the reason is because that's the actual value of Sommerfeld that you have. The value that you created here before stable lubrication was a value based on design, and the Sommerfeld number of 0.0055 was just based on the fact that H0 would be the minimum, which is not the case unless it satisfies stable lubrication as well. Okay, so it depends on the minimum criteria, but it's usually easier to do the second method, and that's why I showed you the second method. Second is because we can continue the problem from there. Okay, we know that our design with Tmax is equal to 95 degrees Fahrenheit has a Sommerfeld number of 0.425, and so that means that for part A, we're going to write that Sommerfeld is equal to 0.425. So now let's go look at what part A of our problem is asking. Okay, part A of our problem is asking, what is the value of the friction coefficient of your lubricant at this temperature if the maximum allowable load is applied to the shaft? Okay, so what is the value of friction coefficient? So we need to find F based on S is equal to 0.425. So we're going to use our charts, and we know that at 95 Fahrenheit, just for clarification, we know that at 95 degrees Fahrenheit, we have a mu of 25.5 times 10 to the minus 6 radian. Okay, that's the viscosity at that temperature, and therefore that yields this 0.425 S that we already found. Okay, so from the charts, we can find R over C times F, and we're going to go look for R over C times F. So I'm going to go look for that really quickly. So we have R over C times F is here. We have L over D is equal to 1. And what we're going to do is we're going to go look for our value at 0.425. So we have a value of 0.425, which is going to be somewhere around here. We're going to go up to the line that is 1, which is going to be around here. And that's going to give us a value of around 8.5 on the left side. So we're going to get a value of around 8.5 on this side. So we're going to choose that value as the value that we look for from chart. Okay, and then based on that, we can rearrange and solve for F. So we have F is equal to 0.017. Okay, the next part, B, is asking, or the next question in our problem is asking to find what is the loss of power due to the lubricant under these conditions? So let's find the power loss. And what we're going to do is, to make it different than the previous video, we're going to find the power loss using horsepower. Okay, so we're going to use HP loss. You could also use BTU per second if you want to, but we'll do the horsepower loss just to change it up. So it's TN over 10,050, which 1,050, sorry, which is in your formula sheet. So first things first, we find torque, which is F times W times R. We have all three, so we have 0.017 multiplied by 300 multiplied by 0.5, and we get that this is equal to 2.55 pound force inches. And then our horsepower loss is going to be the following. So we're going to have HP loss is equal to 2.55 times 1200 over 60 divided by 1050. And we get that this horsepower loss is 0.049 HP. And then part C of our problem says the following. Would you recommend using the setup outdoors in Miami throughout the year? Okay. And the answer is no. Why is the answer no? Because temps can be higher than 95 degrees. So you would need a controlled environment to keep the temperature under 95 degrees, okay? To make sure that you don't run over 95 degrees and could have a problem with your design, okay? So that concludes the problem here. And in the next video, what we're going to do is we're going to do another example problem with a full journal bearing and come up with some decision making based on designs of different journal bearings. So we'll see you in the next video.